So, looks like there's a lot of things today. 2 of those are lessons, 2 are homework. The homework you've had since last week to work on. What we're going to do today is kind of an extension of what we were talking about last time. So, last class we were talking about sine and cosine functions as ways to map positions around a circle during rotational motion. So, if I have a circle, I can talk about my distance left or right from the center in terms of radius lengths or in terms of feet or whatever my length units might be, to describe XY positions around a circle. We had a set of relations and I had some of this drawn on the board. Let me just pull this back up again. But here's the electronic version of it. So if I have a circle with radius r and an angle theta, if I measure that angle in radians, which remember 1 radian arc along the edge of a circle is going to be the same length as 1 radius is. So radians are related to the radius, hence the name. So the relationship between an arc length s and the radius is just, and the angle that forms it is just the length of the radius as a multiplier there. So if I'm talking about measuring in radius lengths, my arc length and my angle measured in radians are going to be the same number. But if I'm measuring in inches, centimeters, meters, miles, whatever I might be measuring in a regular length unit as opposed to measuring in radius lengths, then all I have to do is multiply that angle by the radius length in order to get the corresponding arc length. So this green arc is the length of this radius times however many radians this central angle is. And again, central angles in standard position here from the positive x-axis and going around counterclockwise like we do through our 4 quadrants. That's the first quadrant moving into the second quadrant. Third and fourth would continue, and we can have angles that are more than 180 degrees, but just for purposes of being able to draw this succinctly, I just made a smallish angle. So this is between 0 and all the way around a circle is how many radians? How many radius lengths take you all the way around the circle? 2 pi, right? 2 pi r for any circle size r is the whole circumference. So 2 pi radians is an angle that's equivalent to 360 degrees or all the way around in one circular arc or one circular rotation. It can be a fixed figure or you can think of it as a motion, either one. So I could be thinking about not just like this arc as something that I had to run along, but it could also just be a physical figure and how long that arc length is. It doesn't have to have been traveled through. But a lot of time we use this for circular motion. And so again, the x and y coordinates then use the sine and cosine functions, cosine and sine, I suppose, respectively, to model their position relative to the center of the circle in regular Cartesian coordinates, the xy like grid lines. So you will learn about at some point in time, probably calculus 2, polar coordinates. You might have talked about them before. We might have a chance to talk about them really briefly in here, but it's not one of the topics of the class, and there are a lot of topics in the class, so I don't really want to jam more stuff down into your brain. But when we're talking about lots of circular motion, we can describe locations in circular patterns by distance from the center and an angle. So it takes 2 numbers, but a radius and an angle are going to be sufficient to tell us where we are. And if we're talking about circular motion, it might be easier to track by those 2 numbers as compared to talking about xy coordinates, talking about rectangular coordinates when I'm moving around in a circle, as opposed to moving in a straight line. Using rectangular coordinates is pretty simple. Moving around in a circle, it's kind of a mess. But in any case, we can describe the xy coordinates for position around a circle or the travel around a circle as theta increases. So we can talk about it, again, like I said, as a fixed position, just a location. Or we can also talk about this as motion, and so we can turn these into kind of functions for as theta increases what happens to x and y. But sine and cosine are functions in themselves, but we can think of it just like, oh, it's like a square root function. It does something to whatever you put after it. So cosine of theta takes an angle, theta, and it's assumed to be in standard position. But we're going to talk about how do I deal with what if I have an angle that I want to measure some other direction, or lots of other variations today. But the cosine function takes an input of an angle and tells you relative to this, I mean, we can use it for other purposes, but tells you relative to this, left or right of the center of the circle, how far we are. So a positive outcome from a cosine function indicates we're to the right of the center of the circle, whose angle theta was the input here, an angle in standard position there. If it were something negative, that would mean we're to the left of the center of the circle, so we're in the second or third quadrants someplace in terms of our x value. So x being negative is left, x being positive is right on the axes here. So since the radius of a circle is always going to be a positive number, notice this r here can't be negative. I can talk about, well, what if I'm on the left side? Yep, we're on the left side, but the radius is still the distance from the center. It's an always greater than zero quantity in order to actually have a circle. But the cosine and sine values can come out positive or negative, and so x and y can come out positive or negative. Y values, similarly, we can compute those by finding what's called the sine ratio, the sine of an angle, and multiplying it by the radius. That gives us the vertical distance above or below the center. So the y coordinate of a point like that, how far above the x-axis or how far below the x-axis we are, if the x-axis serves as a horizontal diameter for the circle. So it goes through the center of the circle and it goes all the way across. We can, of course, all of these can be rearranged to just be formulas. One thing can compute another. Each of these involves three quantities, s, r, and theta in the first one, x, r, and theta, and y, r, and theta in the two below. Sine and cosine are like operations, essentially. So if I know 2 out of 3 pieces, I could solve for the third. Solving for theta is not an easy thing. Well, that's going to be one of our last topics of the year. But dealing with all these others, if I know 2 out of 3 pieces, I should be able to solve for the third, because these are equations as well as they could be functions for a theta that's varying like over time. And actually, as I say that, theta varying over time, that's one of the things I want to talk about today. Because if we're talking about moving around a circle, one of the most natural things to talk about maybe relative to that is how fast, not like what angle am I at, but how fast am I moving around a circle, like in feet per second, and how do I make like an amount of time tell me where I am around the circle? Because we can adjust these, because I know how to maybe compute like composition of functions. If I know how much time has gone by, then I know how far I've traveled. If I know how far I've traveled around the circle, I can convert that back to, using the first equation, what the angle is. And therefore I could find an XY position too. So we can start from other pieces of information other than just knowing an angle to find an XY position or to find an arc length. We can start from knowing, instead of an angle, I could know something like speed and amount of time that's passed, distance, rate, and time sort of things. So that's what we're going to work on today, some sort of variations on a theme, but it all goes back to these general relationships between measurements that we can take in a circle to relate angles and positions. So what I want to do today is actually go through lesson 7.4 with you, like the assignment that's in your iMath. Let's see if I can get to this without opening up weird stuff. 7.5 rather. 7.3 and 7.4 were things we talked about last week, but 7.5, this circular motion part 2 lesson. So part 1 is all about the stuff that we talked about last week, just strictly angles in standard position, etc. But let's open this up and talk about modeling circular motion. Again, remembering, I'm going to jot down on the board so I can point to it without taking this down, those relationships that I just had on that Word document that I just drew up real quick. So I had something like, what, angle like this, here's theta, this point on the circumference of the circle that has radius r. I can talk about it by regular xy coordinate points, where x is r cosine of theta, y is r sine of theta. And don't forget that the arc length subtended by angle theta, if I'm measuring theta in radians, is just the radius length times theta. So the circular motion here, what we want to do is, all of the examples in the previous lessons were based on, suppose I have a circle and I start at the 3 o'clock position and I have an angle that's measured in radians, and it's all like kind of preset to be nice and match up with those precisely. Now, that doesn't mean it's easy, but it's the basics of this. We can alter some things and still be able to use sine and cosine, still be able to use our arc length formula. We just have to do a little bit of planning. So, all right, so, and I think that's kind of what this previous, or this first paragraph here actually says. Let me make this a little bigger. In the previous investigation, we used sine and cosine to model circular motion. We looked at radian angle measure starting from the 3 o'clock position, and we're going to continue to do that, but take a look at this first question here, and yours should probably be similar. I think that in the lessons there's very little that varies from one person to the next. So Laura's skiing on a circular ski trail with a radius of 1.4 kilometers. She starts at the 3 o'clock position, so positive x-axis position, and travels in counterclockwise. That CCW, you'll see that in here a few times. I don't think it was used in 7.3 and 4, but it's just shorthand for counterclockwise, just because that's a really long word. Traveling counterclockwise, let's see. Imagine an angle with a vertex at the center of the circular trail that subtends the path that Laura's traveled, and let theta represent the measure in radians. So, it could be this picture. And Laura's traveling around this. It's got a 1.4 kilometer radius. That's the only number we've got so far, well, other than 3 o'clock, which just means that. So, for these two questions, it says write an expression in terms of theta to represent her distance to the right of the center in kilometers, and to write her distance above the center of the ski trail in kilometers. And so all we have just is an angle theta. We don't have a specific number of radians. Doesn't say anything in degrees, it just says theta. Suppose she's traveled through theta. So if I wanted to express her position for part A, what do we have here? This is just review. Expression for her distance to the right or left of the center, however it happens to come out, in terms of kilometers, not in terms of radius lengths. What sort of expression am I going to write for this? If I want to express her distance to the right of the center in kilometers. Yeah?
It'd be 1.4 cosine theta.
Yep, it's going to be like this X statement here. The left or right, however it turns out, for distance to the right of the center. You can always say it's the distance to the right, and if it comes out negative, we'll assume that's left. But yeah, it's going to be this 1.4, or radius, times the cosine of theta. So if theta is something that ends up being the terminal side is somewhere over here, so I've got an angle that's small, first quadrant angle, or something that she's gone quite a long way around the circle, more than 3/4, but not quite all the way around. In either of those cases, I'd get a positive number, and that would mean I'm actually to the right. If I happen to get a negative number, that would mean I'm a negative number for x, meaning a negative number for her distance to the right of the center. That means, oh yeah, so it means left is what that would mean. So just, It's stated here in terms of distance to the right of the center instead of saying something like her horizontal distance from the center, where right indicates positive and left indicates negative. Just tried to take all the wordiness out of that, just like just distance to the right of the center. And if it comes out negative, it means left. All right, so yeah, for that one, if we want to express it in kilometers, not in terms of radius lengths, we need this r here. If it's in terms of radius lengths, it's one radius length. But yeah, so 1.4 times the cosine of theta would tell us her horizontal distance. What about the distance above the center in kilometers, this part B? Oh, by the way, if you want to type in theta, all you have to do is type in theta, and it turns it into a theta. So that's kind of fun. You don't have to use the math palette to do that. Yeah? Exactly. 1.4 times the sine of theta will give you the vertical component of where she is. So the horizontal has to do with cosine, and the vertical has to do with sine. And since our radius is 1.4 kilometers, that's where that comes from in this case. Or just in terms of, if I didn't have that number 1.4 in there, all that would mean is I have a smaller circle radius 1 of something, 1 kilometer, 1 whatever. If I have a larger circle, it's like similar triangles. I'm just scaling this up, so I'm just multiplying by a factor of whatever this radius is to get the equivalent results in larger or smaller circle sizes. I could have 0.6 or something like that for the radius and have something less than 1. All right, in any case then, that's just our basic. If I want to measure a position or describe a position, x and y position or left, right, up, down position, I'm going to use these two relationships. Now, suppose that instead of having an angle as the part that I know, that I have an arc length. Like she knows how far along the trail she's gone because she's got her Garmin watch on or whatever. She's like, oh, I've traveled like 3.2 kilometers along this trail. If we want to know where is she, we should be able to figure that out also. It's just a matter of realizing that, oh, well, if I know my angle, I can certainly find the arc length, which we didn't have to in the last question. We just needed the angle. But if I know the arc length, the distance around the circle, the distance around this circular path that we've traveled, or the arc length subtended by some angle, then I can find the angle too, as long as I know the radius. So suppose she's on a ski trail and let's see, it's still the same ski trail, 1.4 kilometers. She starts at the 3 o'clock position, goes around counterclockwise, and we don't really know the angle because that'd be actually a kind of weird thing to know if you're skiing. If you're like, well, I know that I traveled through 2.6 radians. Nobody's going to know that skiing around a ski trail, right? But you might know how far you went. So if you know that you have gone 1.4 kilometers along this trail, and it's got a 1.4 kilometer radius, how many radians has she traveled through? 1. That's 1 radius length, so that's 1 radian. Or you can rely on this formula for that, but if the radius is 1.4 and the arc length she's traveled through is also 1.4 of the same thing, kilometers in both cases here, then the angle is angle 1. It's like not 1 degree though, this is in radians. So this theta is measured in radians. These are measured in x, y, and r are measured in all the same length units, whatever length units you use. But if one's in meters, then so are the other two, just by doing these computations. But yeah, if she's traveled 1.4 kilometers along this path, that's a circular path with a radius of 1.4 kilometers, then she's traveled 1 radian. What if she's gone 3 kilometers? What computation would we need to do to figure out how many radians, what angle she's traveled through if she's traveled 3 kilometers along the path? 3 divided by 1.4, right? It's definitely more than 1 radian, but a little bit more than 2. It's not a nice round number. But if she's traveled 3 kilometers and the radius is 1.4, if I do 3 divided by 1.4, I can find that angle. So I'll just type in 3 over 1.4. It's a little bit more than 2. I don't know if it'll tell me in number 4. Oh yeah, it's 2.14 something radians. Great. So for part C here, it says write a formula that expresses the number of radians swept out by the angle in terms of the number of kilometers she's traveled since she started skiing. Well, in terms of the number of kilometers she's traveled, I want to be able to express theta in terms of kilometers. So theta is always going to be the number of kilometers she's traveled, that arc length, divided by 1.4, radius in general, but for this circle, if it's the same person, it's just this relationship. If you were thinking about the definition of radians, for part A, you might not have used this formula. You might just say, oh, well, if the radius and the radian length is, or the radius and the distance traveled is the same, that's 1 radian. It's because of this relationship here, or because of the definition of radians, however you were thinking about that. But in general, I can find theta by doing arc length divided by radius. And our arc length is going to change. It's d, this unknown quantity here. Her arc length is going to be changed. The distance traveled is going to change, but it's around the same circle, right? Divide by 1.4. So d over 1.4, or her distance divided by 1.4, is always going to give us the angle she's traveled through. Now, just something that is not necessarily apparent when you're just thinking of a stationary picture, but this angle doesn't have to just be something between 0 and 2 pi, 0 and 6 point something radians. It can be as big as we want. So her distance, she could travel 100 kilometers around this circle. She just have to go around over and over and over again. So she'd go through the same positions repeatedly. But we can talk about the angle that she's traveled through, not just based on a stationary what it looks like location, but she's like, oh, well, just like you can talk about like figure skaters spinning around, like 10 times. Oh, that's 3,600 degrees, or, well, 10 times in radians. 10 times 2 pi would be 20 pi radians. We can talk about angles of rotation as being more than just one full circle, or more than 2 pi, or more than 360 degrees. So that's not like this is limited by, oh, well, this can't be more than such and such. This can have whatever value we want. She can travel as far around that circle as she wants. She'd just be repeating her locations, but she can travel farther and farther and farther. And the angle, we can state the angle as being a really large angle, more than 2 pi or more than 360 degrees. That's okay. All right, so again, traveling around the circle, if I know her distance traveled, which is a pretty normal thing to know if you're tracking what's going on, we can figure out where she is relative to the center of the ski trail. Because, well, I can take her distance traveled and find her angle based on that. So, and this is the lesson, so it kind of has the answer to that afterwards. If she travels d kilometers around the ski trail, the angle is d over 1.4 radians, which means that's also d over 1.4 radius lengths of travel, if you want to think of it that way. But if I want to express based on that again, I'm just going to write this up here. Suppose this is 1.4. And we're calling the distance that she's traveled d. So this is now a picture for this particular problem. If I know that she's traveled d feet around the circle, and this circle has a radius length of 1.4 kilometers, then you can see how we can put the pieces together and model her location based on knowing her distance. So what we had before were functions where the input was an angle and the output was her position. X or Y, depending on whether we're using cosine or sine, right? But what we'd like to be able to do is have different inputs, because I don't always know an angle, although I can find an angle. So it's like this composition of functions. Use her distance to find the angle, and then the angle to find that. But you don't have to do it in 2 steps. You can just write a composite function. So instead of having cosine of theta, I'm going to have a cosine of d over 1.4. So it's cosine of this rearranged thing, because this expression is an expression to compute an angle based on knowing the distance. So I can go from distance traveled to angle relative to the center of the circle, standard position, to x or y by using sine or cosine, cosine or sine. So it's just a matter of using the pieces of information we have to compute something new. It's like composition of functions. It's like a 2-step process. But if you're going to be doing this repeatedly, like if you were asked a bunch of questions about, well, where is she after she's traveled 8 miles, or where is she, or 8 kilometers, where is she after, we could do unit conversions too, but I didn't really mean to get into that. Where would she be if she traveled 92 kilometers and is exhausted because now she needs to be picked up by emergency personnel? We can find this the same way. It doesn't matter what this distance is, we can write functions for any value of distance to find this XY location. So let's see, the actual questions asked here, I think we kind of covered those. Let's see. Horizontal distance in terms of number of kilometers. Oh, so I just wanted to point out the difference between question A and question B here. They're very similar. Write a formula expressing horizontal distance to the right of the center, and we're calling this h, in terms of, for part A, this is asking in terms of the number of radians, and for part B is in terms of the number of kilometers she's traveled. So it's just since she started skiing, and so the first one is just, we're gonna have a theta, and the second one is gonna be a d over 1.4. But the horizontal part is always the cosine, and the vertical position is gonna be our sine function. And so part C is just in terms of number of kilometers d that she's traveled. All right, so let's move on from a ski trail and somebody getting exhausted going around a ski trail. So take a look at this picture. We've got circular motion for sure. If we were tracking someone's motion around a Ferris wheel, tracking something left or right of the center, we could talk about their XY position. The X position is still going to be left or right of the center of the Ferris wheel. But if we're talking about their vertical position, we could talk about how high above or how low below the center of the Ferris wheel they are. But what might be also a normal thing to ask is, how high above the ground are you, right? So we might be interested in that. Now, in terms of on a Ferris wheel, we might be interested in how far you've traveled along the edge of the Ferris wheel, but you're not exerting yourself to do that. You're just sitting in a box. So using just the angle might be normal. We could talk about the angle or the distance traveled around the edge of the circle, though either one, we know how to do that. But like I said, what might be kind of more interesting to track vertically speaking, or in terms of y, is not necessarily maybe just how high you are above the center or how low you are below the center of the Ferris wheel, but how high are you above the ground? Which varies here. So suppose in this picture, I've got this Ferris wheel. It says the radius is 8 meters. The center of the Ferris wheel is 12 meters above the ground. Think for a second, just this isn't one of the questions that's down below. At least I don't think it is. But think about for a second, while you're on the Ferris wheel, what's the range of heights above the ground that you're gonna go through? While you're on the Ferris wheel, not while you're waiting to get on it, but while you're on this Ferris wheel, what's the minimum height above the ground and the maximum height above the ground that you're gonna have? So again, this is a circle with a radius of 8 meters, and the center of the circle is 12 meters above the ground. So while you're on the Ferris wheel, what's the closest to the ground you're gonna be? What's the lowest height above the ground you're gonna have? In meters. Yeah, I see, I see a couple of fours. Yeah, 4. So this is 8 meters here, and 12 meters all the way from the center down to the ground. So that's gonna be 4 meters above the ground there. So that's pretty high. There must be like steps going up to it. You're not jumping into this. What's the highest above the ground you're gonna be when you're up at the top of the Ferris wheel? Yeah, 20, because it's gonna be 12 up to the center, and then if you're all the way at the top, that's an extra radius above, so up to 20. So in terms of height, now just remembering sketches that we did, when we drew a sine function, which was about the vertical motion. Our general sine function kind of went like this. So our y value, when we started at 0, just on a circle centered at the origin, we had a y value of 0, that by the time we were halfway around the circle would be back to 0. Halfway around the circle would be pi radians. And then by the time we're all the way around, 2 pi radians as our angle, we'd be back to 0. And how high or low we go depended on how big the circle was, but 1 radius above or 1 radius below the center of the circle, which was on the xy axes then, it's symmetric in any case, regardless of how far that is. So, if it's 1.4 or 8 or whatever. Now, this circle has a radius of 8 meters, right? Yeah. So let me put these back to how they were originally. S equals r times theta, x equals r times cosine of theta, y equals r times sine of theta. And this is r, call this s, there. Now it's back to a general picture. So in general, if I wanted to track motion around a circle that had a radius of 8 meters, I say, oh, well, radius of 8, y equals 8 sine of theta. Or in other words, this would go up as high as 8 and down as low as -8 meters, if that's the units of measure that I'm using. So if I pick a measure for r, like a unit for r, kilometers, meters, inches, millimeters, whatever it is, y is going to come out in those same units. This is just that ratio that we're talking about. So if I just say, oh, y equals 8 sine of theta, this goes between 8 and -8. That's distance above or below the center of the circle. If I want to talk about distance above or below, well, it's not going to be below, distance above the ground, and the center of the circle's 12 units above the ground, 12 meters. Any thoughts on what I could do to alter this function, which is pretty close to what we need, to make it go, instead of between -8 and 8, to make it talk about things that are between 4 and 20, or in other words, be 12 units higher? Think about what we did at the end of chapter 6. Yeah,
You got 12.
just add 12, right. If I want to shift something up by 6 units, whether it's a parabola, graph-wise, or anything else, I just want to add 12. Or in terms of this question, or in terms of just thinking about our relationships, this tells me the height above or below the center of the circle. If I want to know the height above the ground, well, I just need to know the center of the circle is 12 meters higher than the ground. So if I just add a plus 12, not into the sine function, but just take this whole output of this sine function that tells me the height above or below the center of the circle, and then add 12 to that. That makes every value 12 bigger than it used to be. Graphically speaking, that takes this graph and shifts it up 12 units, just like if I graphed y equals x squared versus y equals x squared plus 12, that plus 12 at the end just moves it up. If these are all moved up 12 units, 12 added onto this, 12 minus 8 is 4, 12 added onto that is 20. That's our between 4 and 20, like we wanted. You don't have to think about this in terms of that wave graph, but that is what this is. This is still just adding on to a function. If I had a graph of that function, all I would do is make it not go above and below the x-axis equally. It makes it all move higher. So, now, let's see. There are some other questions here. Let's go through these questions. The actual questions asked here: if she's traveled 4 meters along the path of the Ferris wheel, how many radians is that? Let's see. 4 meters. I wish I could pause this, but I can't. If I'm traveling 4 meters around here, and the radius is 8 meters, 4 meters here, 8 meters there, that's half a radius length, so it should be a half radian that she's traveled. This is just kind of a review question, but she's gone through half a radian. If she traveled 45 meters along the path, then I know that she will have gone through, well, 45 divided by 8. Lots of radius lengths, right? 45 divided by 8 is 5 point something. 5.625 apparently, radians. So if I wanted to model, like I said, traveling around a Ferris wheel, unlike skiing, you might not really know how far you've traveled. You could certainly track that though. But the angle that she's gone through, measured in radians, based on the fact that she's traveled d meters, and this had a 8 meter radius, we could always say d over 8 for that. But going on to this other question. So if I wanted to know her height above the center of the Ferris wheel, in terms of theta, that's just about relative to the center of the Ferris wheel, all right, not the ground. That's just, height above or below, that's just y equals r sine of theta, right? So y equals 8 sine of theta. And again, just if you want to type theta, theta, that gives you a theta symbol on here. You can also get to that using the little yellow arrow in the trig functions. Wait, does it show it in there? I thought I had a theta in there too. Maybe it doesn't. Okay, well then make sure you remember to type theta. I think it probably says that somewhere in the instructions here. Now, if I wanted to say this in terms of how many meters she'd travel around, if she'd traveled d meters around with a radius of 8, that's d over 8. So we'd still have this sine expression if we're talking about the vertical. Let's see. Oh, write an expression for her height. Sorry. So her height based on angles, or her height based on number of meters traveled around the circumference of the circle, or meters traveled in her basket around the Ferris wheel. But if I want to talk about her height above the ground, that's where the plus 12 is going to come in, because the ground is 12 feet below the center of the circle, or the center of the circle is 12 feet above the ground, or her height above the ground is going to be 12 more than, and you can put it at the beginning or the end, 12 more than what her height relative to the center of the circle is. So this one asks for her height relative to, in terms of D, the number of feet she's traveled. When I wrote this before, it was in terms of the angle that she traveled through. But we can use either one. So just 12 more than 8 times the sine of, well, theta, or d over 12, or d over 8 rather, the distance traveled around the edge of the circle was this d. S is usually the length used for arc length, but just to have a specific number for Kristen, we picked some different letter. But it's just 12 more than that. So you can put the 12 plus at the beginning, if that makes more sense. It's 12 more than something else that I already figured out. So I'm just going to add 12 to that. But in terms of, like I said, graphs, which we're not going to do spend a lot of time graphing in here. You'll have some graphs in here, which are kind of fun, because it lets you kind of work with the symmetry of these, or the repetitiveness of them, to make the graphs. Now, if the center of the Ferris wheel is 12 meters above the ground, then I'm going to go above and below that, so that after she's gone all the way around, 2 pi radians, she's back to that 12, but she hits that 12 meters above the ground at the beginning, measuring from the 3 o'clock position, halfway around from there, back to where she started. But in reality, on a Ferris wheel, when you think about starting on a Ferris wheel, if you're not like up in the air a quarter of the way, you probably think about, well, I started at the bottom and went up from there. So there's some other things we can talk about in terms of adjusting these functions as well, to adjust for, we don't have to always start at the 3 o'clock position. In addition to things like, well, I don't have to measure by angles, I can measure by distance traveled around the circle. I don't have to measure relative to the center of the circle, I can measure relative to something else that's higher or lower than the center of the circle. So I can add or subtract, something like this. The adjusting other ways is a little bit more difficult than adjusting just vertically. We're going to have to adjust like how fast something goes around, if we're talking about speed. Or we can talk about like kind of shifting this left or right, so that this, maybe I start at the bottom. I maybe want the bottom to be at the beginning. And those are some of the trickier things to do. But let's talk about time first, because that's, getting the starting position is kind of less important than getting this to go around the right speed. Because if you're skiing at a constant speed, maybe not as likely as going around a Ferris wheel at a constant speed. But if you're going around in a circle at a constant speed, if you're given the speed that you're traveling at and the radius of what you're traveling around, you should be able to calculate distance. And if you can calculate distance, you should be able to calculate angle. So it's like one more step in this composition of functions. So this is an example here with a bunch of toy cars traveling at various speeds. They're obviously all going to go through the same sorts of patterns. These are at different distances from the center of the circle. They're like on a racetrack, and the one on the outside is going really fast. So fast as even traveling around a circle faster than the other ones, even though it's got a longer path. But if we know a speed, an amount of time we've passed. I can use the amount of, let's see, here, let me put it this way. So if we have a constant speed given, and we know how much time has gone by, then we can calculate distance. And if we can calculate distance, we can calculate angle, and if we can calculate angle, we can calculate position. So it's like one more step in this compositions of functions. So you can see these are all going, like, let's just say they start in the regular 3 o'clock position and go around counterclockwise, not to do anything tricky with that. Just thinking about how we can start from knowing speed and an amount of time as our independent quantity. Time is varying, speed's constant. Let time go by. What distance, angle, and x and y value do we have based on that? So car A, that's the one in the center in this diagram here. Car A is 2 feet from the center of a racetrack, travels at a constant speed. And on here, instead of giving us the speed, it just says the angle with the terminal ray passing through car A goes through 1 radian per second. Oh, well, it's an angular speed that we've got here, that not a linear speed. But if we're going through 1 radian every second, how many seconds would it take to go all the way around 1 loop? If we go through 1 radian per second, approximately how many seconds would it take to go all the way around once? Yeah.
6.28.
Yeah, 6.28. 1 radian per second to go all the way around is about 6.28. It's 2 pi radians. So regardless of how big the radius is, if it's 1 radian per second, then it takes 6.28 seconds to go all the way around, right? So if I have my speed measured that way, these questions here, how many radians does the angle sweep out in t seconds? Well, it says 1 radian per second. So if t seconds have gone by, then that'd be 1 times t, otherwise just known as t, right? If it's 1 radian per second, then in 2 seconds it's 2 radians, 3 seconds, 3 radians, 5 seconds, 5 radians, and so forth. So in that case, like t would match up with our theta that we had before, because it's just 1 times that. The angle measured, it's an angular speed as opposed to like a more normal sort of speed. You might think of miles per hour sort of speed. We're talking about radians per second, but that's kind of a starting point. We're going to be adjusting to do these sorts of things. What goes in here? What goes in that spot? Just like we did before when we were saying, well, what if I have the distance traveled instead of the angle? Well, I can compute that. So if I wanted to find a function to determine the distance to the right of the center, okay, so horizontal distance, that's x. It's going to be our cosine function. Distance to the right of the center of the racetrack is a function of the number of seconds. Let me put these back to standard instead of other stuff I've used them for. X equals r cosine theta, y equals r times sine of theta. But our angle is the same as 1 times t, or just plain t, the number of seconds. I don't have a radius of 1, however. I have a radius for car A of 2, right? So in terms of my horizontal distance relative to the center of the circle, I'm going to have 2 cosine of, not theta, but just of t, right? I can put 1t in there if I want to. But 2 cosine of t would be the horizontal position, just as r cosine of theta idea, but theta is equal to t based on our computations in the first part. So we already answered part C. That's the first question. 2 pi radians is 1 full rotation. At 1 radian per second takes 2 pi seconds to go all the way around. But take a look at this graph. We're going to do some graphs here. So this is a graph of a cosine function in general. It's this right here. I've got t along the horizontal axis. So that this is time going by, time in seconds at 1 radian per second means I start at 2 meters to the right. Is it meters? Feet, sorry. 2 feet to the right. And then by 2 pi seconds, I'm back in that same position. And so kind of piecing together a graph like this, because you're going to have to do a clip to graph. So if you know where the beginning and the end of one loop are around the circle, or one period, or one travel around the circle, 0 to 2 pi, you can say, oh, well, then the middle, the bottom, would have to be halfway between those two at pi. So if I were graphing this, and I'll show you how the graphing works on this in just a second. There's some graphs to do down here. If you can pick, it'll put like a wave graph together for you. You just have to click a couple of points. If you can click the top and the bottom of a wave, it'll put the rest of it in place for you. So if you know where the beginning and the end of a full loop are, you can find the middle, the opposite end of that wave, by dividing that value in two, or visually, just where it's halfway between where you started and stopped. All right, so in any case, though, on this, we started 2 feet to the right. By the time pi seconds had gone by, because we're going at 1 radian per second, that's the same as pi radians going by. We're on the opposite side, 1 unit to the, or 2 units to the left, down at -2 of the center of the track. And then by the time we're at 2 pi seconds, that would be 2 pi radians we'd travel through. Since it's 1 radian per second, we're back at 2 units positive, so 2 units to the right of the center of the track. All right, so in this diagram, car A was the closest in. Car B is out farther. It also seems to be going a bit faster. So car B, 2.5 feet from the center of the racetrack, travels at some constant speed where it's moving at 2 radians per second. So it's still this angular speed that's given. We don't have like a meters per second or feet per second sort of speed. We have radians per second still. But car B is 2.5 feet from the center of the racetrack, going at 2 radians per second around this track. See if you can figure out how many radians does it go through in t seconds. So theta equals some expression in terms of t. Find a function g to determine the horizontal distance from the center, the distance to the right, where negative would be to the left, as a function of this number of seconds. And then part C asks, how many seconds does it take to complete 1 full lap? And that's going to be important for us doing our graph. So see if you can figure out parts A through C, and then I'll show you how this graph works. So this angular speed is 2 radians per second. All right, so what we really want for A then, how many radians do we sweep out after t seconds? So like after 1 second, 2 seconds, 3 seconds, how far have we gone around this circle? If you're confused about what to do, think about those a few specific number examples. So after 1 second, if t is 1, this is supposed to be going through 2 radians per second. So if t is 1, I should have 2 as my number for theta. 2 is the angle, 2 radians. After 2 seconds, it should be 4. After 3 seconds, it should be 6, and so forth. So however many seconds have gone by, theta should be 2 times that. The angle in radians should be 2 times the number of seconds. So the angle in radians, theta, should be 2 times the number of seconds, 2t. So in terms of writing out these expressions for horizontal or vertical position, if I were going to write either of those, I know, oh, instead of theta, if I want to write this in terms of the number of seconds that have gone by, I'm going to write 2t in those spots. And then the other thing, our radius. This car B is traveling with a radius of 2.5 feet from the center of the circle. So if I'm going to track its, let's see, distance to the right, horizontal distance, this is going to be our cosine function. 2.5 times the cosine of 2t. All right, so instead of r cosine theta, my r is 2.5. Theta I can compute by doing 2 times the number of seconds that have elapsed. So this part C, the angle with the terminal ray passing through car B must go through 2 pi radians to make 1 full rotation. Okay, as through any car. It goes through 2 radians per second. So how many seconds does it take to go all the way around 1 full lap? Pi? Yeah, just pi, right? Because 2 pi radians is the angle. If I want to know how many seconds that is, we had in this one, oh, I don't have that specific relationship written down. Oh, it's part A. Theta is 2t. If theta is 2 pi, what's t? Oh, 2 pi divided by 2. So it'd be pi seconds, or about 3.14 seconds to go all the way around. It goes through 2 radians every second. So to go through 6.28 radians would take a little bit more than 3 seconds, right? But you can also just use this first equation, theta equals 2t. If you know theta, you can find t. If you know t, you can find theta. It's not just a function, it's an equation that you can use to solve knowing one value to get the others. So this graph then, it takes pi seconds to go all the way around for this car. Right? So between time 0, this is t, time on the horizontal axis, between time 0 and time pi, it's going to go all the way around. At the beginning, it's 2.5 units to the right of the center. And by the time I get back to pi units, it's also going to be at that same height. But I can't make this graph here. I'm going to click and make a graph. But I know I have the first dot, that's at the top. If I could put a second dot at the bottom of the curve, so halfway between those 2 peaks, halfway between, it's all the way to the right. I know it goes down somehow and goes back up. It's going to be at its minimum halfway between those 2 peaks, right? It's nice and symmetric, so the bottom is halfway between the consecutive tops of the waves. So halfway between 0 and pi is pi over 2, and at pi over 2, I'm going to be down at negative 2.5 feet to the left of the center. So I just clicked those 2 points, the top and the bottom of the curve. There's the other way to graph these curves is to graph it shows the center and the top, but if you can see the little red dots on this template that's selected here, it shows a bottom and a top of a curve. So if you select a bottom and a top, which would be like not the beginning and end of a full cycle, but the beginning and halfway through, then it will just fill in the rest of it for you. So it's kind of nice to be able to do that because it helps you see how the beginning, end, and center are related, but you don't have to do all the tedious sketch it yourself. So it's a little bit more useful than just punching a formula into a calculator and seeing it all at once, because you get to think a little bit. But I don't really want you doing a bunch of plotting and playing, well, where would this go? It's not very easy to draw these, but you can see that this x-axis stays, halfway between the tops and the bottoms of the curve, or it goes just as far positive as it does negative. This isn't like the Ferris wheel where it's all positive values. I have positive values indicating to the right of the center of the track and negative values indicating to the left of the center of the racetrack. But again, all we did to graph that, if you can find, so you can graph different ways, but if I check this here, it wants a top and a bottom. It doesn't matter what order you do them in. So, the highest is 2.5. The lowest is negative 2.5. And that doesn't happen at pi units is all the way around, so halfway is where my lowest is going to be. All right, last one on here that I want to go through, and this one I'll leave for you to try on your own more. We'll talk about it afterwards, but car D is 3.5 feet from the center of the racetrack, and it goes through pi radians per second, so that sounds faster, 3 point something radians per second. So same sorts of questions. How many radians does it sweep out in t seconds? Write a function for its distance to the right of the center. How long does it take to complete one full lap? And then there's sketch a picture. Well, sketch with your computer. It's the same track here that has, let's see, we've got this car is 3.5 feet from the center. This is the outermost car. Just gonna scroll it for a second. So after we're finished with this one, I want to add on one more that has a more traditional sort of speed mentioned. Oh, sorry. A piece of paper someplace. Don't worry about it. All right, so let's take a look at this. Car D, 3.5 feet from the center of the racetrack, going at a constant speed of pi radians per second. So after t seconds, how many radians have we traveled through? Pi t, right? So after 1 second would be pi, after 2 seconds would be 2 pi, 3 seconds would be 3 pi, because it's pi radians per second. Not a very nice number, but relative to a circle, that's not that bad. So if I'm thinking, well, how much is this? After 1 second, pi radians is halfway around the circle. After 2 seconds, 2 pi radians, all the way around the rest of the way. 3 seconds, 4 seconds. You can maybe picture how fast this is going. But pi times t And notice I just typed PIT and it worked. But if you put a time sign in there, oops, that works also. All right, so if I want to find a function, we're calling it j, for its distance to the right of the center, in terms of a function of the number of seconds since the start of the race, what do we have for this car? J of t equals, let's see, horizontal distance is cosine, so r cosine theta is what we want. 3.5 cosine of pi t, because we had theta is the same as pi t. All right, so the angle with the terminal ray passing through car D must sweep out 2 pi radians to make 1 full rotation. It goes through pi radians per second, so how many seconds does it take to complete a full lap? 2, which is nicer numbers than on our graph. Weird things in our expression here, but 2 seconds times 0 to 2, it'd go through 1 full lap. Meaning it'd go from 3.5 down to negative 3.5 and back in 2 seconds. So that means at 1 second, that's when we're all the way to the left. Or you could maybe track that, because although it's a weird number, 1 second means you've gone pi radians or to the other side of the circle. 2 seconds means you're back to where you started. 3 seconds is back to that other side of the circle again, and so on and so on. So our graph of this would look like this. This is the position relative to the center of the circle over time. Now, let's talk about what if I had a regular speed. So these were 1 radian per second, 2 radians per second, pi radians per second, angular speeds. What if I had, and this is a bit more of a challenge, last thing for the day though, suppose I had a linear speed. I had a number of, what was this measured in? Feet per second. So what car did I not use? Car C? I think we had this track here. Yeah, car C we didn't use. We used car A, B, and C, or A, B, and D. We're 2, 2.5, and 3.5 feet from the center. So let's say I've got car C is 3 feet from the center. Or it's traveling along a path with a 3-foot radius. And let's say that it is traveling at a speed, not in radians per second, but let's say that it's traveling at a speed of something in feet per second. Let's say that it goes 1 foot per second. Instead of like a number of radians per second. It goes 1 foot per second. So let me ask a couple of questions kind of like this. If it's traveling at 1 foot per second, how many radians per second is that? Another way to think of that, 1 foot is how many radius lengths? I know how many radius lengths 1 foot is, then I know how many radians this travels through every second. So the answer to both of these questions is the same number. What number is that number? For car C, which has a 3-foot radius, or is traveling around a circle with a 3-foot radius. 1 foot is how many radius lengths? Yeah, it's 1/3. So 1 foot per second traveled around the arc is the same as 1/3 of a radius length traveled along the arc per second, or 1/3 radian per second. And I abbreviated this. Let me write out radian. But 1/3 radian per second means the same as 1/3 of a radius length, arc lengthwise, per second. Remember, those mean the same thing. So if this is traveling at 1 foot per second, that's 1/3 of a radian per second. So let me ask the other question that he's asked. How many seconds does it take to go all the way around? One-third of a radian per second. How many radians is all the way around? 2 pi, or 6-ish, right? So if it's about 6 radians all the way around, how many seconds about, just like estimating? 1/3 of a radian every second. So it takes 3 seconds to go 1 radian, right? So to go 6 radians would be like 18-ish seconds. What operation are we doing there? It's the same one we did before. If I want to know the relationship between S, R, and theta, arc length traveled, radius, and theta, all the way around is 2 pi. I know what my radius is. Oh wait, what were we doing? What do we have? How many seconds to go all the way around? So in previous question, how many seconds to go all the way around? We're going 2 pi, let's see, 2 radians per second, which means it takes pi seconds to go all the way around. So it's 2 pi radians all the way around. So I want to know 2 pi. If I divide it by my speed here, that's how I can get that pi. 2 pi divided by is all the way around. We divide it by 2 to get pi seconds. Now let me put the rest of the units in here. This is radians per second from the previous problem. This is radians. Radians divided by radians per second give us seconds. That was at 2 pi radians is all the way around. We're doing 2 radians per second, so it takes pi seconds to do that. Like distance equals rate times time sort of thing, but we're solving. Same thing here, only we've got 1/3 of a radian per second instead of a whole number, 2 radians per second. So if I have 2 pi divided by 1/3, I'm going to get 6 pi seconds to go all the way around, or about 18-ish seconds to go all the way around. You can get an estimate and then maybe like figure out what you need to do just by saying, oh, 2 pi, that's about 6. If we're dealing with things that aren't multiples of pi. So 2 pi is about 6. I go through 1/3 of a radian every, oh, not minute, second, sorry. 1/3 of a radian every second. So 3 seconds means I've gone through 1 radian. 6 seconds is about 2 radians. To get through about 6 radians, it's going to take about 18 seconds. This is 18 point something, probably maybe even 19 by the time I've rounded off that much. But 6 pi would be the exact answer for that. But in any case, in terms of our expression here, if I wanted to write an expression for its position at any point in time, I just need my speed. I can do this as before. So 1/3 radian per second, just like this 2 radians per second means I've got this 2t thing going on here. 1/3 of a radian per second would be the equivalent of having like 1/3 t here. So I'd have 3 cosine of 1/3 t for the equivalent with this. I don't have a typeability of that. But this car C, if I wanted to track its horizontal position, it's got a radius of 3 feet. So its horizontal position, so its x value is 3 times the cosine of, well, in terms of time that's gone by, I'll use t variable as before. Of this 1/3 t. It's going at 1 foot per second, which is 1/3 of a radius per second. So t here, if this is a number of seconds, then 1/3 t gives me the number of radiuses, which is the same as the number of radians. So this is a kind of extended beyond what you see in this lesson here, but you don't have to have angular speed. You can have linear speed along the arc also. Miles per hour, feet per second, instead of like radians per second. Those sorts of things. It just takes this same conversion between distance traveled and radians traveled between s and theta, using the radius in order to convert between those two. So we can go from an amount of time that's gone by to a distance along the arc, and that distance we can convert into an angle, and that angle we can get x or y from that using sine or cosine or sine, respectively. All right, so that's it for today. We'll talk some more about the complexities of 7.5 or 7.6, which is actually some of what we were just talking about. On Thursday, we're going to kind of extend this a little bit, but yep, more circular motion next time.